When people ask how big the universe is, the question sounds simple, but the moment we try to answer it, we run into a problem that has followed astronomy for centuries. Human intuition evolved on a small planet. We understand kilometers, buildings, and landscapes. We do not naturally understand distances so large that light itself needs millions or billions of years to cross them. So the real challenge is not only measuring the universe, it is learning how to think about scale in a way that makes sense. The best way to approach this question is not to jump immediately to giant numbers. Instead, we start close to home and move outward step by step. Every layer of distance changes our understanding of what big actually means. Earth is about 12,700 kilometers wide. That sounds large from a human perspective, but in space, it is small enough to disappear quickly. The Moon, our closest neighbor, orbits at an average distance of about 380,000 kilometers. Even this first step already stretches imagination. If Earth were reduced to the size of a coin, the Moon would still be several meters away. Now, move one step farther. The Sun sits about 150 million kilometers from Earth. This distance is so important that astronomers created a special unit for it, the astronomical unit, or AU. It gives us a practical ruler for measuring distances inside the solar system. Earth orbits at 1 astronomical unit. Jupiter is about 5 astronomical units away. Neptune, the outermost major planet, is roughly 30 astronomical units from the Sun. But the solar system does not end with the planets. Beyond Neptune lies a vast region filled with icy objects, and far beyond that, a distant cloud of comet-like bodies known as the Oort cloud. If it exists as we expect, it may extend tens of thousands of astronomical units from the Sun. At that scale, the Sun is no longer a bright, dominating object. It becomes just another star among many. Already we see something important. The space between objects is far larger than the objects themselves. Space is mostly emptiness. At some point, kilometers and astronomical units stop being useful. Distances become too large. That is where light becomes our measuring tool. Light travels at about 300,000 kilometers per second. In 1 second, it can circle Earth more than 7 times. In 1 minute, it travels 18 million kilometers. In 1 year, it covers almost 10 trillion kilometers. This distance is called a light year. A light year is not a measure of time, it is a measure of distance. It tells us how far light can travel in a year. The reason astronomers use it is simple. The universe is so large that ordinary units become meaningless. Light from the Sun takes about 8 minutes to reach Earth. That means we always see the Sun as it was 8 minutes ago. The nearest star beyond the Sun, Proxima Centauri, is about 4 light years away. Even at the speed of light, the journey would take more than 4 years. For spacecraft moving at current human speeds, it would take tens of thousands of years. This reveals another key fact about the universe. Stars are not packed together like cities on Earth. They are separated by enormous distances. Even in our local stellar neighborhood, space is mostly empty. Our Sun belongs to a galaxy called the Milky Way. From Earth, we see it as a faint band across the night sky, but in reality, it is a massive rotating system containing hundreds of billions of stars. The Milky Way is roughly 100,000 light years across. If you could travel at the speed of light, crossing it from one side to the other would still take 100,000 years. Our solar system sits far from the galactic center, about 26,000 light years away. The Sun orbits the galaxy just like planets orbit the Sun. One full orbit takes around 230 million years. Since Earth formed, the Sun has completed only about 20 of these galactic years. Even at this scale, the pattern continues. The stars themselves are tiny compared to the empty distances between them. If the Milky Way were reduced to the size of North America, our entire solar system would be smaller than a grain of dust. For a long time, astronomers believed the Milky Way might be the entire universe. That idea changed in the early 20th century, when observations revealed that some faint spiral shapes in the sky were not gas clouds inside our galaxy, but entirely separate galaxies. Suddenly, the universe became much larger than anyone expected. The nearest large galaxy, Andromeda, lies about 2.5 million light years away. Light reaching us today left Andromeda before modern humans existed. Andromeda and the Milky Way are part of a small collection called the Local Group. containing dozens of galaxies bound together by gravity. When we look farther out, we see that galaxies gather into clusters. Clusters combine into superclusters. On even larger scales, the universe forms a vast structure known as the cosmic web. Galaxies are arranged along long filaments stretching across space, separated by enormous voids where very little matter exists. This structure did not form randomly. It emerged from tiny density differences in the early universe that slowly grew under gravity. At this point, it is natural to ask how far we can see. The answer leads us to one of the most important ideas in cosmology: the observable universe. The universe has existed for about 13.8 billion years. Because light travels at a finite speed, we cannot see objects farther away than light has had time to reach us since the beginning of the universe. This creates a horizon, not a physical boundary, but a limit to what we can observe. At first glance, you might expect the observable universe to have a radius of 13.8 billion light-years. But the real number is much larger. The reason is that space itself expands. While light travels toward us, the space between galaxies stretches. As a result, objects that emitted light long ago are now much farther away than the distance the light originally traveled. Today, the observable universe is estimated to be about 93 billion light-years across. That number represents the region from which light has had time to reach us since the beginning of cosmic expansion. Beyond this observable region, the universe may continue. We simply cannot see it yet. There is no evidence that space ends at the edge of what we observe. The limit exists because of time and the speed of light, not because of a wall or boundary. This leads to one of the most common questions: does the universe have an edge? Current observations suggest that, at least on large scales, space appears remarkably flat and uniform. A flat universe could extend infinitely. It could also be finite, but so large that its curvature is impossible to detect with current measurements. Scientists do not yet know which possibility is correct. Measuring these enormous distances requires careful methods. Astronomers use a series of techniques known as the cosmic distance ladder. Nearby stars can be measured through parallax, the tiny shift in position as Earth moves around the Sun. Farther away, astronomers use objects with known brightness, such as certain types of exploding stars called supernovae. By comparing how bright they appear with how bright they truly are, distance can be estimated. For extremely distant galaxies, scientists measure redshift. As space expands, light stretches toward longer wavelengths, shifting toward the red end of the spectrum. The greater the redshift, the farther the object and the faster it is moving away. This observation led to the discovery that the universe itself is expanding. Another key source of information is the cosmic microwave background, faint radiation left over from the early universe. It provides a snapshot of the cosmos when it was only about 380,000 years old. By studying its patterns, scientists can infer the overall geometry and size of the observable universe. When we step back and look at all these scales together, the question, how big is the universe, becomes more nuanced. We know the size of the observable universe because we can measure the light that reaches us. But the total universe may be much larger. It could be finite, yet unimaginably vast. It could be infinite. Current data cannot give a final answer. What we can say with confidence is that the universe is structured, measurable, and understandable through physics. From Earth to the Moon, from the solar system to the Milky Way, from galaxies to the cosmic web, each level reveals a larger pattern built on the same fundamental laws. Perhaps the most surprising realization is how small the region we directly experience really is. Everything humans have ever observed with the naked eye fits inside a tiny fraction of our galaxy. Everything recorded in history happened on a planet orbiting one ordinary star among hundreds of billions. And yet, through careful measurement and patient observation, we have learned to map distances that no human will ever travel. We can look billions of years into the past simply by observing distant light. In a sense, astronomy allows us to turn distance into time, transforming the sky into a record of cosmic history. So, how big is the universe? The honest answer is that we know part of it. The observable universe, stretches about 93 billion light-years across. Beyond that, the cosmos continues into regions we cannot yet see. Whether it ends somewhere far beyond our horizon or extends forever remains one of the largest open questions in science. What makes this question powerful is not just the size itself, but the perspective it gives. Each step outward changes our understanding of scale. Planets become small, stars become points, galaxies become grains in a larger structure. And still, the universe keeps expanding beyond what we can observe. In the end, the size of the universe is not a single number, but a boundary between what we can measure and what remains unknown. Astronomy continues to push that boundary outward, one observation at a time.